With Kroger brand products from Baker's, you can make all your favorite things this holiday season. Because Kroger brand's proven quality products come at exceptionally low prices. And with a money-back quality guarantee, every dish is sure to be a favorite.
These are a few of my favorite things.
Whether you shop delivery, pickup, or in-store, Kroger brand has all your favorite things. Baker's, fresh for everyone.
Today's show is brought to you by ExpressVPN. Protect your online activity today and find out how you can get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Visit tryexpressvpn.com/space to learn more.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello again, and thank you for joining us. This is the podcast known as Space Nuts. I'm known as Andrew Dunkley, and Fred is known as Fred, of the Watson variety. Astronomer at large. Hello, Fred.
How are you doing, Andrew? It's good to know what you're known by, because it's better than knowing what you're known for.
I've been called many other things over the years, and late for dinner as well. Now, this week in episode 127 of Space Nuts, we're going to talk about a dust cloud that's orbiting Earth. I knew that space was a dirty place. Why does it have to hone in on us? I mean, it's filthy enough here already. But something we've talked about before is the Parker Solar Probe. It's now making its final approach to the sun, so things should start happening rather fast. Get your barbecues out. And we've got a couple of questions. One from Clem asking about tremors in telescopes. Telescopes are a favourite topic of Fred's because he wrote a book about them. And another question from Christopher asking if life is likely to be standardised across the universe, biologically speaking, or could there be other forms of life not based on what our form of life is based on? I think that's where he's coming from. We'll try and tackle all of those questions and more on Space Nuts. But first, Fred, this dust cloud that's enveloping us and making a mess of our little piece of the solar system, what's this all about?
Well, you're quite right that space is pretty dusty, and actually, we particularly here well, let me put it this way, particularly for you up in regional New South Wales, where you've got fairly dark skies. You can see that dust every night almost when there's no moon around, because there's something called the zodiacal light, which puzzled astronomers for quite a long time as to what it was. But we now know that this is the light from dust in the solar system. It's something you can see after sunset or before sunrise. It's like a pillar of light that is sort of standing above the sun. I've seen it many times because, of course, Siding Spring is a very dark place, so we don't have much light pollution. But that's living proof, if you like, of the fact that the space between the planets is quite dusty, because that pillar of light is just essentially the sun illuminating the disk of dust that is around it, so the dust in the plane of the Earth's orbit. But this story is about something a little bit different, and it's about the way that dust can congregate, because back in 1961, which you won't remember, but I do very clearly.
I was -1 that year.
There you go, -1. Well, you missed a good year. It was a good year, was 1961. A Polish astronomer whose name was, I think I'm pronouncing this correctly, Kazimierz Kordylewski.
Sounds good.
He was basically proposed the notion that there would be clouds of dust in gravitationally stable points in the Earth-Moon system. So what do I mean by that? Well, you and I have talked about this before. These are the Lagrange points. And Lagrange was a 19th century mathematician who proposed that there would be, if you've got any two gravitating bodies, for example, the Earth and the Moon, there will be positions around them where their gravity combined with the rotation of the Moon around the Earth, where they would conspire to produce what you might call neutral points where there's no pull of gravity. And the first one of them, the one we call L1, the first Lagrange point, is really easy to get your head around because it's between the Earth and the Moon, and you can intuitively imagine that, if somewhere between the Earth and the Moon, there's going to be a point where their respective gravity balances out.
And it wouldn't be halfway unless the gravity of both bodies was equal.
The same. That's correct. Absolutely. So it's much nearer the Moon than it is to the Earth because the Earth has the greater gravitational power. But there are 4 other of these stable points sort of dotted around the space between or the space around the Earth and the Moon. And 2 of them in particular are of interest because there's a lot of astronomical phenomena that essentially centre on these things, and they rejoice in the name of L4 and L5, the 4th and 5th Lagrange points. They're sometimes called the Trojan points because they actually attract asteroids in other contexts. Let me digress briefly to explain that. If you think about the planet Jupiter going around the Sun, 60 degrees ahead of Jupiter in its orbit. So what's that? That's
yeah, well, don't ask me.
No, it's a sixth of the way around. To do the calculation, God, it's a bad day. A sixth of the way around its orbit ahead and a sixth of the way around the orbit behind. There are 2 of these stable points, the Lagrange points, and they actually collect asteroids in the case of Jupiter and the Sun. So Jupiter's got this clump of what are called the Trojan asteroids preceding it in its orbit, and another clump of likewise named Trojan asteroids trailing behind it, 60 degrees behind it in its orbit. So that's why they're called the Trojan points.
Right.
Okay, that was a digression. Now think about the Earth and the Moon again. So there are 2 Trojan points, one ahead of the Moon, one behind, a sixth of the way around, as we've said, 60 degrees ahead and behind the Moon. And what Dr. Kordylewski proposed was that those points, because they're stable gravitationally, they would be a place where dust would congregate. Just the dust in the solar system would tend to accumulate there. And he actually believed he had photographic evidence of that. In other words, he took photographs of the space 60 degrees ahead of and 60 degrees behind the Moon and thought he could see a brightening. But it was not terribly convincing. So there the story languished until now, basically, because a group of astronomers, not based actually in Poland, but based in Hungary, they are at, I love the name of this university, the Eötvös Loránd University in Hungary. I hope I'm pronouncing that correctly too. Its scientists there have done a double whammy on this. They've published 2 papers in that august journal, the Monthly Notices of the Royal Astronomical Society. It's actually one of the leading professional astronomy journals in the world. They've got 2 articles in there, one of which basically builds a theoretical model of these dust clouds and says that, yes, the theory does predict, exactly as Kordylewski said, that there would be clouds of dust in these positions relative to the Earth and the Moon. But the second paper is about observations they've made of not both of these, but one of them, I think it's the L5 cloud that they've observed. And it's really interesting observations. So, of course, what you've got to do is choose, first of all, a site where the sky is very dark, so no artificial light. You need to be well away from twilight, so there's no light from the sun in the sky. You need to be well away from moonlight as well. So you want the moon, below the horizon. Probably at the time of new moon is the best time to do this. And then you look at the place where you expect to find this dust cloud. So they've done that. They have found a brightening of the sky there. But more especially, they've identified something else that is kind of the smoking gun for a dust cloud.
Let me guess, an intergalactic lounge chair, because there's always dust behind one of those.
You're almost on the mark there, Andrew. Because I can't even think of the way you could relate it to reality. It's not the fact that you've got an intergalactic lounge chair. It's that you've got your polarizing sunglasses on. It's all about polarization. And so we have means of measuring this property of light. So, when you look at things in space, you can measure their color, their brightness, but you can also measure their polarization as well as the spectrum. Of course, that's the distribution of color with, the intensity with color. So you can measure polarization. You use a very specific and rather sensitive piece of equipment called a polarimeter. And a polarimeter is really just a glorified pair of polarizing sunglasses. I know the polarimeter specialists in the world would be reacting with horror at that statement because they couldn't be more different. But the principle is the same. What you're doing with polarization is you're trying to isolate the particular way in which the light waves are vibrating. So what's called unpolarized light, which is kind of what's all around us most of the time, is light that's vibrating in many different planes, in an infinity of different planes, really. But if you are wearing polarizing sunglasses, for example, what you then do is just isolate one of these planes of vibration. And the reason why you do that with sunglasses is because the light from a reflecting surface, like a body of liquid or a brightly lit road, is highly polarized. So that allows you to just select one way, one of the ways in which the light vibrates. Now, we know that dust in space actually polarizes light. And so that is one way of detecting when when you're actually looking at dust rather than just something else that's brightly illuminated in space. And that's the smoking gun in this case. So these Kordylewski dust clouds, the one that has been observed by these Hungarian astronomers, shows strong evidence of polarization, which tells you that you've got a cloud of dust there rather than, a cloud of gas that's just illuminated or just self-illuminated, right. Something of that sort.
So what they've thought was there all along is basically what we've found out through polarization. Just a couple of thoughts, though. How big are we talking in terms of this dust cloud and what's likely to happen to it long term?
So yeah, that's right. The dust cloud itself is probably bigger than the moon. It's it's a fairly what's the word? It's certainly not a dense area of dust. It's reasonably tenuous. There is motion of the dust particles themselves within the cloud, and that anything that's got this sort of excited motion about it tends to be bigger if it's made of particles. These, in a sense, what's happening is these individual dust particles are in orbit around the Lagrange point, which sounds a bit weird. How can you be in orbit around nothing? Well, gravity lets you do that. Yeah. But the other thing that these scientists have done is to model the way that this dust cloud is being replenished from the general dust within the inner solar system, and to try and get a measurement of how long it will last. In other words, what its lifetime is. And it looks as though it's a fairly stable feature. It probably will last for many billions of years.
Unless my wife finds out about it and she's up there with her vacuum cleaner, and that's just the way she swings.
But, as I've said before, Andrew, I'm not going there.
But we have an answer in astronomy at last.
We have an answer in astronomy, that's right.
You're listening to Space Nuts. Andrew Dunkley here with Fred Watson. Now, let's take a little break and find out more about our sponsor, ExpressVPN, rated #1 by TechRadar. This is the one I use. I've been using it for a couple of years and I love it. When I joined ExpressVPN, they were brand new to the market, but I read a lot of reviews and did a lot of comparisons. And there was just something about their business model that I particularly liked. And a couple of years down the track, honestly, can't complain. Their interface is very easy to use. Their service is second to none. I've had to contact them a couple of times about certain things that I wanted to do, and they were brilliant. So you may be wondering why I do need a VPN at all. It's all about privacy. Do you really want big tech companies, governments and others knowing what's going on with your online activity? Even if you're having nothing to hide, it just feels downright creepy. I think you'll agree. And governments are getting more and more interested in what you're doing every day. And so, yeah, protecting your privacy is what VPN is all about. And how often do you run across websites that you want to get information from only to find that they're geo-blocked? This is becoming an increasing problem, but ExpressVPN solves that problem for you. Now, if you go to our special URL, you'll see quite a list of things this service can help you with, things you may never have thought of before. As I say, it's the one I use, secure, fast, and it just works. So protect yourself online today and find out more about how to get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Try expressvpn.com/space to learn more, and you'll find the link details in the show notes and on our website. Now, back to the show.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Now, Fred, we head towards the sun and we revisit something we talked about a couple of months ago, which was the Parker Solar Probe, which was launched. Well, it's now approaching its destination. That's the fast part of the project, literally fast. We'll talk about that too. But now it's got years and years of work to do.
Indeed, that's right. So its destination is a series of orbits that will take it ever closer to our parent star, to the sun. The Parker Solar Probe is designed to answer some of the really deep questions about the way that the sun works. I might list them in a minute, but the bottom line in terms of the news at the moment is that after a successful launch on the 12th of August, not that long ago, you and I spoke about that. It has now actually broken a record because it has become the closest human-made object to the sun, and it will continue breaking that record throughout its mission, which goes for almost 7 years. So at the moment it's within 40 million kilometres of the sun. Remember, that compares with the 150 million kilometres that we are away from the sun here on Earth. So there it is on its way inwards. It's also herring along at a fairly fast rate, something in the region, certainly relative to the sun, in the region of 70 kilometers per second, which is significantly faster than you and I can move most of the time.
Yeah.
Even when you allow for the 30 kilometers per second motion of the Earth, which is taking us around the sun. So yeah, it's really knocking on. You might remember, Andrew, that I think we commented on this when the spacecraft was launched. It's a relatively small spacecraft. Its mass, as launched, is something like 700 kilograms, a little bit less in fact, but the payload itself is only 50 kilograms worth. That's the stuff that does all the measurements. So relatively lightweight, but it was launched on one of the most powerful rocket launching machines available to US scientists, the Delta IV Heavy. And the reason for that was to get it into this solar orbit as rapidly as possible, because you need to go fast in order to get into the inner solar system.
Yeah, well, when we talk about years of travel to get somewhere, it's not very often we get the opportunity to talk about a launch and then a couple of months later and say, well, they're there.
It's there, yeah, that's right. But in a sense, being there is just being in a particular orbit rather than rendezvousing with a specific planet. I mean, we talked a week or so ago about the Bepi-Colombo spacecraft launch, and that's on its way to Mercury, but it's going to take 7 years to get there, with 9 planetary flybys on the way, because it's rendezvousing with the fastest planet in the solar system.
And this is where it all gets really weird in the minds of many people. We can send a probe to the sun in a couple of months, but we are going to take 7 years to get to Mercury, which is orbiting the closest to the sun. It's just all, and people go, what? I mean, how is that possible? But it's all about the speed, isn't it?
It is. It's what you're trying to achieve as well. You know, the Parker Solar Probe will wind up in an orbit that is not trying to rendezvous. You know, it's not trying to slow down to go into orbit around Mercury, for example. It'll whiz by Mercury really very quickly. Its mission is all about understanding big questions about the sun. One of them is, well, I suppose the biggest of them all, is why the corona of the sun, which is its outer atmosphere, why is that so much hotter than the surface of the sun that we see? And of course, that surface is not solid. It's a layer of glowing gas, but we call it the photosphere. That surface is at a temperature of somewhere in the region of 5,500 to 6,000 degrees Celsius, whereas the outer corona of the sun is at a temperature measured in millions of degrees, about 10 million degrees. And it's not obvious how that gets so hot. It's actually, once again, very tenuous. It's a very rarefied gas, is the gas in the solar corona. But still, there must be some mechanism that causes heat transfer to warm it up. And that's not really understood. So the Parker probe will go at least some way towards investigating that. We also want to know how the solar wind gets accelerated to the kind of 1,000,000 km/h speeds that it blows at. And this is the wind of subatomic particles that the sun emits all the time. They bathe the inner solar system. When they get particularly energetic, we start seeing aurorae here on Earth. But we don't really know why that wind of particles should be so fast. It's almost certainly all about magnetism, and so the structure and dynamics of the magnetic fields in the lower regions of the sun's atmosphere are also targets for the solar probe to investigate.
So we could start seeing answers fairly rapidly? Or
Yeah,
at least data, maybe not answers.
Yeah, we won't see images because this spacecraft kind of hides behind its heat shield, which it'll need to do because its closest approach to the sun takes it within 6 million kilometres, which is, almost skimming the surface of the sun.
Don't stick your hand out the window, basically.
That's right. Yeah, that's right. So it's got a fairly heavy-duty heat shield to protect the spacecraft itself and its instruments. There's nowhere to poke a camera through, so there won't be close-up photographs. So there are other spacecraft already in orbit around the sun that can do that very well. But what the solar probe will be sensing is the magnetic fields and particle densities and things of that sort. So I hope we'll start seeing those relatively quickly.
Okay. How much danger is it in? I mean, it being in that proximity to the sun and getting up close and personal, is it in a precarious zone?
In a sense, it is, and that's why the heat shield itself is heavy-duty industrial strength carbon composites.
And Hollywood wants its Iron Man suit back, so yeah.
Yeah, that's right. Like most space missions, Andrew, the early phases will be relatively conservative in what they will expect the spacecraft to do. So the mission consists of 24 orbits around the sun over the next 7 years, getting gradually closer and closer to the sun. So its first, passage across the surface of the sun will be relatively benign in the sense that it's not going as close as it will at the end. As I said, the 6 million kilometre range at the end of the mission is going to test the heat shield to the ultimate, but you don't do that kind of thing right at the start of the mission. You want to get all the data you can from it in those early phases and then do the audacious stuff towards the end, which is what this mission's all about.
And then crash it into the sun.
It will actually wind up being permanently in orbit around the sun. It won't melt, but it will almost certainly, cease to operate because its electronics will get fried by subatomic particles and things of that sort.
It'll just become a chunk of metal.
It'll be space debris, space junk. That's right.
Oh, that's interesting. We've never done that before.
It's not like us, is it, to do that, to leave stuff like that?
And I've just done my mental calculation, and it's travelling at 690,000 kilometres per hour.
That's when it passes closest to the sun. That's right.
Will be. But in American, it'll be slower, 430,000 miles an hour. We in the metric world are much faster than you in America.
Just to put it into context, that's 190 kilometres per second.
Ouchie mummers. That is fast.
Yeah.
It's very fast.
It's about 120 miles per second.
Well, as soon as there's something to know, we will certainly let you know here on Space Nuts. You're with Andrew Dunkley and, of course, Fred Watson.
3, 2, 1.
Space Nuts.
Now, Fred, a couple of questions. This first one comes from Clem Unger. Hi, Clem. Thanks for sending us your question. You've hit on one of Fred's favourite topics. He actually wrote a book about telescopes. Now, Clem asks, all large Earth-based telescopes employ adaptive optics to eliminate atmospheric effects on the images and thereby can achieve amazing resolutions beating Hubble. With the new super telescopes in the pipeline with mirror diameters over 30 metres, isn't there a point where Earth tremors become a problem and affect the imaging? Is there an effective way of compensating against this in use or under development? Great question.
It is a great question, and Clem's absolutely right that certainly what you might call the VLT generation of telescopes, very large telescopes. The VLT is the name of the 4 big telescopes down in Chile, operated by the European Southern Observatory, but we sometimes talk about them being in the 8-metre class, and the 8 to 10-metre class is the biggest class of telescopes in operation today. And by that I mean optical telescopes that use visible light. So they do employ this technique of adaptive optics, and what that is all about is using something a little bit like the way noise-cancelling headphones work. You pick up the distortions in the light from a star as it comes through the Earth's atmosphere, and then you correct for it. And they use flexible mirrors, in fact, to do that. So mirrors with lots of computer-controlled actuators behind them. And these are quite small. They're only a matter of a few centimetres across. They're in the optical path that comes from the giant mirrors themselves. But they sense the incoming wavefront, as we call it. That's the way that the light itself comes from the stars or galaxies or whatever you're looking at, and they sense the shape of that as the atmospheric distortions alter its shape, and then they correct for it. And that's really clever stuff, and it's working very well in some of the world's largest telescopes. So the question about the stability of the telescope itself is a very good one, because the last thing you want is to have these sensitive devices being spoiled by vibrations of the telescope.
And he brings up a good point when you consider that some of these optical telescopes are in quite shaky parts of the world, Hawaii, right, and the southern American regions. They're all very volcanic.
Yes, in Chile, and that certainly it has been an issue for some of them. Now, just to preface this, all telescopes of any size, and in particular the ones that are in Chile and Hawaii, which is exactly as you've said, are earthquake-prone regions, they're all built with compliant features in them. So by that I mean that they've got things that will break rather than allow the Earth to shake the telescope. So you can sort of imagine that you've got this telescope on its foundations. If it was totally rigid, then the earthquake would probably shake the telescope to bits, or at least to destroy its fine alignment and things of that sort. But there are these compliant or things that will actually break. Fusible was the word that comes to mind, but that's in connection with a similar problem with steam engines. They used to put a fusible plug into the firebox so that if the temperature got too high, it would melt and put the fire out. And it's a similar sort of safety feature that you've got on the telescopes. If there's enough shaking, it will break these links, and the telescope itself will stay put while the ground shakes underneath it. But that's really all about very large-scale tremors. For vibrations in the Earth itself, which you can imagine might come from heavy vehicles moving around, or from the dome of the telescope itself moving. Domes of these things weigh hundreds of tons, and as they move, they tend to set up vibrations. So there are already damping mechanisms built into the telescope. What you usually do when you build a telescope is you put the pier of the telescope down onto the ground, you fix that firmly, and then you build the building around it and make it vibrationally isolated as much as you can. So that vibrational isolation is now perfected to a very high level, and that's why you can actually build 30-meter telescopes, 30-meter class telescopes, with adaptive optics that are not being detrimentally hampered by Earth tremors. I mean, a big tremor will break the links, and that's all fine. But small tremors will not actually affect the way things are handled.
So yes.
So
Clear.
yes. There is a point at which Earth tremors are an issue, but they don't affect the imaging because it's dealt with in the design of the telescopes.
Very good. Okay, hope that helped you out, Clem. Great question, by the way. Now we move on to a question from Christopher Pooley. Now, Christopher's got a very interesting question about life. We've talked about life before and the possibility that, or the probability now that it exists elsewhere. It's just a matter of us finding it. Given what we know about the universe, it is safe to assume that physics works the same throughout the universe as it does on Earth. It is also safe to assume that chemistry is the same based on various scans and samples taken by robots and telescopes. Can you tell me if astrobiologists think that biology has or works the same way? Or even could work the same throughout the universe. You've explained that they are looking for certain markers that they believe spawned life on Earth, but are there any other things they are thinking about? I'm not talking sci-fi, but are there any theories that life could exist in another way other than the ways that we know of now, as in our own carbon-based life form, I guess what he's getting at. Thank you, Christopher. That is a brilliant question. David Duchovny portrayed this once in a science fiction comedy film where the life form that invaded Earth was based on a completely different element on the periodic table, and you could kill it with anti-dandruff shampoo.
There you go.
Now, I mean, that was a joke, but that's probably a fair point as to where Christopher's headed.
It is. That's right. And yes, this is it's a question that astrobiologists do ask themselves. What forms could life take? Of course, one of the difficult issues here, Andrew, is how do you define life? What is a living organism? One definition is that it is a self-sustaining, self-replicating entity that is capable of Darwinian evolution. But there might be machines that could actually do that.
We're starting to build them, aren't we?
We're starting to build them, that's right. So are they alive? That's a great question. All sorts of definitions. Another one is a living organism is something that modifies its own environment. That's rather interesting too. It's a very broad one. But I think what we do in astrobiology is, first of all, look for life of the kind that we know. And that's why there's such excitement about water being so common throughout the universe. Water is, of course, the working fluid of all life on Earth. All earthly life relies on water. So that's a good starting point, because then we know that there is at least one example in the universe of such a life form, or such a class of life forms. But it needn't, it needn't blinker you as an astrobiologist to looking at other possibilities. And perhaps the closest example of this to home is that people have looked at the frigid lakes and seas of Titan, the largest moon of the planet Saturn. That body has these liquid seas and lakes. It's the only other place in the universe besides the Earth where we know that there is a liquid on the surface in equilibrium with its atmosphere. Those lakes are made of hydrocarbons. They're made of ethane and methane, and they're liquid because of the low temperature out there in the region of minus 190 Celsius. People have looked at the possibility of there being life forms that use those hydrocarbons as their working fluid. In other words, liquid natural gas. And yes, such things could exist. So you're already in a region where we're well outside our terrestrial experience, but scientists are open to the possibility that they could be, living organisms. And I think their properties have been fairly well studied. The kind of kind of properties that such a microbe might have, an ethane-based microbe, for example. And then people have looked at things like, well, okay, we are carbon-based life. Carbon has the property that it tends to form huge masses of large complex molecules, and they can be arranged into all kinds of interesting things like DNA and RNA and all of those things that are associated with life. What about other elements other than carbon? Silicon is one that's often been nominated as, that there might be silicon-based life forms out there. And we do know actually of large complex molecules or bodies of molecules of silicon which exist here on Earth. We call them rocks because rocks are made of silicates.
And people have pet rocks?
And they do have pet rocks, yeah. They don't say much or do much, but there you go. They're probably not capable of Darwinian evolution either.
Possibly not.
But that's a slightly, perhaps a slightly comical example. But the bottom line is, yes, you've got to look at all possibilities. And I would not mind betting that when and if we do find life beyond the Earth, it will take us by surprise, because it will be something quite different from what we've been expecting.
It'll be a squid. It's always a squid. I've watched enough science fiction to know they always default to the squid.
That's the default situation. That's quite right. But anyway, the main thing is that we are keeping our minds open about this sort of thing, and I think it's what makes it really interesting, that you never know what we might find.
Yes, indeed. So, Chris, all options are open, and thank you for your question. It does remind me, Fred, of a little thing that was doing the rounds on the internet some years ago. It was a viral email of this race that was touring the universe looking for life, and they came across Earth. And they suddenly realised that we were three free-thinking lumps of meat, and they basically decided, well, that's just not on, so they just avoided us.
It's not like something else.
Meat computers. They just couldn't get their metallic heads around it. It was beautifully written, very beautifully written. It's probably still doing the rounds. And if you want to go and look for it, I'm sure you'll find it. Fred, fun as always. We covered a lot of topics from the sun to dust clouds to fast travel. Tremors in telescopes and the possible biology that exists in other parts of the universe. It's a very broad spectrum program today.
A truly nutty one.
Yes, indeed. Nuts are life too. And we will see you next time. Fred, thank you so much.
It sounds great, and I look forward to it, Andrew. All the best. Take care and have a good week.
That's Fred Watson, astronomer at large, joining us every week on Space Nuts, as you do too, and we really appreciate it. Thank you, and we will catch you next time.
Space Nuts. You've been listening to the Space Nuts podcast. Subscribe to the full podcast on iTunes, Audio Boom, and Stitcher, or your favourite podcast distributor. This has been another quality podcast production from Bytes.com.